So আমাদের এই কোয়েশ্চেনটা আছে যে we are given this table wait, we are given this table and we have to find the effort, time and the person month. So if we are given one table, so it will be the basic Cocomo. So the formula of basic Cocomo is that to find the effort, we have the formula is AB into BB to the power, no sorry, control Z the K log, the kilo lines per code to the power BB. So here we are given LOC is equals to 80,000. So kilo LOC will be 80,000 divided by 1000, that will be 80. Now AB, so it says the project is embedded mode. So for embedded we see the AB is 3.6, so we will use 3.6 here, and 80 to the power for embedded BB is 1.20, so we will use 1.20. So if we calculate it with the calculator, we'll get 3.6 into 80 to the power 1.2. The answer is 691.85. So the answer is 691.85. So now that we have the effort, we'll next calculate the time. So for basic Cocomo, the time is CB into e to the power dB. So here we'll find the value of E, and for embedded mode the value of CB is 2.5, so we write 2.5 over here, and we'll use the 691.85 to the power 0.32. So the value will be 2.5 into 691.85 to the power 0.32. The value is 20.26. So the value is 20.26. And next we'll find the person month. So finding the person month, so we can write this as 21 is it months? Oh, I have to check, wait. So for person month we have to, the formula is E divided by T. So this gives us 691.85 divided by 20.26. the result is 34.14. Now if we look to the slide, so wait, pause my. So if we look at the slide, we'll see the unit of each one. So the unit of E is person month, the unit of time or duration is months, and the unit of person is persons. So let us make those changes here. So this is person per month, and this is months, and this is 35 persons. So we are done with this problem. So now let's see how we can find the total function points. So for this example, we are given the weights of each operation, for simple input operation, for average input operation, complex, and we are also given how many inputs. So for simple inputs we have 10 simple inputs, we have 5 average inputs and 3 complex inputs. So we have to multiply these with these values and then sum them up. So let's start. So we have to multiply this with 10, this with 5, and this with 3. Next, the output. So this multiplied with 8, multiplied with 12, and multiplied with 2. 3 multiplied with 10, 5, 5 into 10 into 5 into 0. So you have to notice if these are in the same order, the files might be in this place and inputs might be here, so pay good attention when reading the question. So now we have to sum these, then after that we have to sum all of these. So korbo eta naki beshi aje eta. So 3 into 10 plus 4 into 5 plus 6 into 3, this will give us 68, and we will get similar for then 4 into 8 plus 5 into 12 plus 7 into 2. So after we get all these values, we sum them up and we get the total unadjusted function point. So if we see one of our slides, we will get a better idea. So first, this example, we see the total unadjusted function point is 338. Next, what we have to do is we have to calculate the adjusted project complexity. So there is a rule for this. So here it says that if our system is simple, then we use 0.65. If our wait, let me annotate it. So if our project is simple, we use 0.65. If our system is medium or normal, we use this value, and if we have a large or a complex system, then we use 1.35. So if we go back to the last slide, we see here we used 0.65. so this is a small project, and this 0.01, this is a fixed value, so this doesn't depend on anything. And in the question you will be given a project complexity, the total processing complexity. If you are not given the total processing complexity, you have to assume that it's 0. So in our case, in the last question, we didn't have the processing complexity, so we have to assume it's 0. And after we find the APC, the adjusted project complexity, in this case it's 0.72, we multiplied the APC with the total unadjusted function point to get the TAFP. And using the TAFP, on the next slide we can
calculate the clear lines of code.
We can calculate the lines of code. So in the last example we saw that we can do a lot of things with lines of code. So in this example we see that how we can calculate the lines of code from scratch. So this, and you will be given a language. So you might be also given a language where you code 75% of your code in C and 20% the rest of the 25% in C++. So your then lines of code will be 75% C, so we use the value here 130 plus 25% of C++. So 25% out of 100 into, for C++, the approximate number of lines is 50. So this will give us the lines of code for this system where we use 75% C and 25% C++ for coding. So the question might be changed in a lot of ways. You just have to keep a steady mind. So that's it for this problem. Now moving on, one start. So for this problem, let us read the question. We have the depth of inheritance, the value is given 4 over here. The number of operations added to the inheritance, NMA, the value is 5. The number of inherited operations is 3. Number of inherited operations is NMI is 3. And the NMO, number of overloaded operations, is 4. So the formula is NMO into DIT divided by NMI plus NMA plus NMO into 100. So if we put the values, the NMO is 4 multiplied by DIT is 4 divided by NMI 3 plus NMA 5 plus 4. So we get the answer, which is 4 into 4 divided by
16 by 12.
3 plus 5 plus 4. 4 by 3, but 1.33. So the answer is 1.33 or 133 into 100. The formula also has this 100 and I missed that, so the answer is 133. So this is the specialization index. Correcta pause mara uche. Acha, now let us look at cyclomatic complexity. So this is the formula. So let's say we have a graph. Wait, I need to enable drawing. So let's say we have a graph and we have a bunch of nodes over here. So how many edges do we have? E is the number of edges. So here we have 1 2 3 4 5 6 7 8 8 edges. And how many nodes do we have? We have 1 2 3 4 5 6 7 7 nodes. Okay, and P, which is here, it says the number of connected components. P is mainly how many cycles do we have in this graph. So as these lines are both these lines goes both ways, so we can have a cycle like this, we can have a cycle like this, and we can have a cycle like this. So there are 3 cycles in this graph. So the value of P here is 3. And if we just calculate with this formula, we will get M, which is the complexity. So this is a this is the cyclomatic complexity calculation, and it might come in a different way. And also I need to clear some things about the cycles. So let's say you don't have bidirectional edges, you have single directional edges. So if you look at this picture, you have this this cycle going clockwise, and there is another cycle going clockwise, but this we don't have 3 cycles here, because if we want to make another cycle, this doesn't support it. So we have only 2 cycles here. So you have to be careful if in the question there is bidirectional graph or a single directional graph. Also, this question might come in form of কি বলে ওটাকে 110 করতাম না flowchart. So in a flowchart you might have loops. So p is the number of loops. So you might have n is equals to 10, then if I is greater than 0, I is 10. So you give a loop over here. No, yes. So yeah, and no. So here you see you have to make these edges, nodes and edges, and you have to count. So this is a node, this is a node, this is a node, this is a node, and this is a cycle. So you can also do the math in that way. So this was it for cyclomatic complexity. Now moving on, our next topic is this detect removal efficiency. So here the formula is really simple. What's DRE? A defect is found when an application does not wait, I'll use the drawing tool. So a defect is found when the application does not conform to the requirement specification. A mistake in coding is called error. So the average DRE score is usually around 0.85 across a full testing program. So here DRE, so to find the defect removal efficiency, which is the short form of DRE, you are given the defects and you are given the error. So here the defects is 100, which is D. Now the error is 100, which is E, and after the release 5 defects are found. So D is 5. So if we put those values in the formula, so we have the error 100 divided by error plus defect, so this gives us 0.95%. so this is a good value because it's better than the average, right? So a value less than 85% would be a bad value of DRE. So that covers this topic. So now let us look at defect density. So defect density is the number of defects identified divided by size. So here size is considered as a requirement. So it can be the number of requirements. So here we see we have 5 requirements and 30 defects. So for this example, the defect density will be 30 divided by 5, which is 6. Could be easy. And for the next slide, we have to look at fan in, fan out. So basically what fan in is the number of different modules calling a specific function. So this is fan in. So fan in is good, right? So it makes the program more modular. You're using, say you have a function named sum, right? So different parts of your program, different parts of your system is using the same function over and over again. So this is ensuring reusability. So fan in is good, but fan out is bad, because what fan out means that a single function or a single module is calling multiple different functions. So when this function is called, this module has to wait, this function has to wait for this function to return a value, then it calls this function and this calls this function. So fan out is really bad for this whole system. So you can read these in the slide or not, whatever. Now next, so if you are to
Identify fan in and fan
identify
out.
fan in and fan out for each of the activities or each of the functions, say this has a fan in of 1 and fan out of 0, in of 1 out of 0, fan in of 1 out of 0, in 1 out 0, this one in 1 out 3,
In one, out three.
in 1 in 1 in 1 in 1 in
In one.
1. This has in 0 and out of 1 2 3 4 5 6 7, out of 7. So this was fan in and fan out. I'll cover another topic in this video, and the last topic. Oh, video চলতেছে না? Oh, আচ্ছা ঠিক আছে. So now let us look at an example of intermediate Cocomo না দোস?
হ্যাঁ
এটা intermediate Cocomo না?
হ্যাঁ
Intermediate Cocomo. So in intermediate Cocomo you will be provided with 2 tables, right? So here you have AI BI. So
sorry,
earlier
basic
the formula was for effort AB into k log to the power. আচ্ছা আমি কেন মাউস দিয়ে লিখতেছি, আমার তো পেনই আছে, পেনটা কই গেল, একটু পজ দেই, পেনটা হারাই ফেলছি।
দেখ এআই বিআই তো নাই,
AIB আছে
ইন্টারমিডিয়েট
আছে আছে।
ও আচ্ছা
So
আচ্ছা আচ্ছা ঘুম আসছে, আমি কিছু বুঝতেছি না।
so in basic Cocomo we use this formula AB into k log to the power BI, but in intermediate Cocomo instead of this AB and BI we use AB and BB, we use AI and BI, and we also multiply the total effort with EAF, and here EAF is given. So the value of EAF will be normally given. And next we will also have to the next part is same as it was for the basic Cocomo. So this part is unchanged, and only part that changes is the first part. So moving on, this is এটাকে কি Cocomo বলে, I don't know. So this is some maths you have to study. So let's say you have been given that a person gives 25% effort in a 9-month project. So he gives 25% into 9, so 2.25% months. Now a 25% effort means that he gives, so if we divide 24 into 1/4, we get wait, pause mari. Hey those. So guys, what I found out is that this isn't actually a math, it's just a normal things, but any basic things said to understand the topic, but the maths is in the next slide. Here is the maths, so let's look at it. If a person works for 8 hours per month and there are only 2 weekly holidays, then what will be the effort given in percent? The project will be finished in 9 months. How many percent per month do you need to complete the project? So if a person gives has 2 weekly holidays, so a month has 30 days, and we have 4 weeks in a month, and we get 8 holidays. So we have 22 working days. So here is the 22 working days, and he works 8 hours per month, so in a month he totally works 176 days. But in a month there are 30 days and there is 24 hours in each day, so 30 into 24, this gives us 720. So out of the 720 hours, he works 176 divided by 720 into 100 will get the percentage of his effort. So his effort is about 25%. And if we want to so the project will be finished in 9 months. How many percent month you need to complete the project? Acha, how many person per month? Acha. So if that person works for 9 hours and completes the project, then that person is giving a total of 2.25% month. So this is solved to this example. Now let us look at another example. So here it says that x, oh wait, let me use the drawing tool. So x value, x is the daily working hour. Daily working hour is 8 and weekly days off is 1. So let us find the total working hour in a week. So month, working hour in a month, working hour in a month equal, so 8 into 30 minus, so he has 1 day off, so we have 4 weeks in a month. This gives us 8 into 26. This is the work per month done by that person. 8 into 26, this is 208. So now we have to find the percentage of his effort. So percentage effort in a month, per month, percentage effort per month equal 208 divided by 30 into 24, which is 720. So this gives us 208 divided by 720. This gives us 0.2888. Now this is close to 29%. Okay, so what is the person month? So y is the person month, x is the percent effort. So the percent effort, the value of x is 29, not the percent. So the value of x is 29, and we have to find the value of y. So y is person month. So to find the person month, we have to multiply the percent effort into the number of months that he worked. So he worked for 9 months, so 29 0.29 into 9, so that gives us 9 into 0.29. The answer is 2.61% month. So this is the answer. So I hope you enjoyed the video, and I also had fun making this video. I hope you do fine in whatever you do in life, and I will be thanking Norwaz Junaid to spend his valuable time with me. মানে I wouldn't have done it if no one was there with me. So thank you, Norroz. তুই কি জেগে আসছ এখনো?
তো সানো জেগে গেছে। থ্যাংক ইউ আমানত ফর ইউর টাইম।
Thank you, দোস। আল্লাহ হাফেজ।
থ্যাংক ইউ ফর হ্যাভিং